Hi everybody. So this lecture is about section 11.3, again on inference about two means. In this case we're going to study independent samples. Unlike what we did in section 11.2, we were talking about dependent samples. So we'll be using the t-distribution again in this case, although the test statistic will be slightly different. So the objectives in this case will be to test hypotheses regarding the difference of two independent means, and construct and interpret confidence intervals regarding the difference of two independent means. So a couple things, preliminary things we should talk about here is if you're talking about the sampling distribution of the difference of two means with independent samples, with population standard deviations being unknown, this is called Welch's t-test. But suppose that a simple random sample of size n1 is taken from a population with unknown mean mu1 and unknown standard deviation sigma 1. In addition, a simple random sample of size n2 is taken from a population with unknown mean mu2 and an unknown standard deviation of sigma 2. If the two populations are normally distributed or the sample sizes are sufficiently large, then this test statistic can be used. And so this will approximately follow students' t-distribution. In this case, the degrees of freedom will either be n sub 1 minus 1 or n sub 2 minus 1 degrees of freedom, whichever one is smaller. And then in this case, xi bar is the sample mean and si is the sample standard deviation from population I. So x1 bar is the mean sample mean for n1, and x2 with the bar over is the sample mean for n2, etc. So the first objective we want to talk about here is to test hypotheses regarding the difference of two independent means. And this procedure is listed in the purple box on the bottom of page 555 and the top of page 556 in your book. So let's go through that. So the first thing is that you'll have to have, again, the conditions are met. So here are the conditions that need to be met in order to use the test. So again, the samples obtained are random. Again, samples are independent. The populations from which the samples are drawn are either normally distributed or the sample sizes are relatively large. In other words, both samples have to be greater than or equal to 30. And then for each sample size, the sample size is no more than 5% of the population size. So again, we have three types of tests: two-tailed, left-tailed, right-tailed. And again, we've got our alpha level, which will again be given to you, typically 0.05%. Here's the test statistic again, which we just looked at. So compute that test statistic, and then it depends on whether you're using the classical approach or the p-value approach. As in the classical approach, again, you use table 5 or stat crunch. Again, in this case, using whichever degree of freedom is smaller, since the t-distribution will depend on the degree of freedom. And again, either the test statistic will fall in the critical region or it won't. Again, if it does fall in the critical region, you will reject the null hypothesis. And then with the p-value approach, again, you're comparing the areas again. So again, use table 6 or stat crunch again, or something else to compute the p-values, or determine roughly what the p-values are. Again, you have 2 or 3 types of tests. And again, the instructions on how to use the technology for this section are on page 566 at the bottom, depending on what you're using. And again, as usual, if the p-value is less than your level of significance, alpha, reject the null hypothesis. And then again, don't forget to state the conclusion clearly. Okay, so let's look at an example here. But before we do that, I should mention that these procedures are robust, which means that if there's a slight departure from normality, it won't adversely affect the results. However, if data have outliers on your box plot, right, the procedure should not be used, and we'll have to rely on non-parametric tests, which we'll talk about later. So let's look at an example here. So a researcher wanted to know whether state quarters had a weight that is more than traditional quarters. So he randomly selects 18 quarters that have state logos on them, like Wisconsin and things like that, or Minnesota, and quarters quarters and 16 traditional quarters, and you weight each one of them and obtain the following data, right? So I think this is data we've seen before. Now again, because these two samples are not matched paired, they don't necessarily have to have the same sample size. And again, remember that the t-distribution will depend on the degrees of freedom or the sample size that's smaller, right? So in other words, whatever many samples we'd have here, subtract 1, and that will become the degrees of freedom. So we want to test the claim that the state quarters have a mean weight that is more or greater than traditional quarters at the 0.05 level of significance. So this should be a right-tailed test. And again, you have to check to make sure that the population is normal, since the populations are smaller than 30 in this case. So again, not anything you'll have to worry about, or that information should be given to you. And I guess you might be able to look at this and kind of determine whether the two samples are relatively the same, but again, you should really rely on the test statistic. So again, here's our test. So again, we're checking to see whether the two means are equal, right? The average weights are equal, or if the state quarters weigh more than the traditional quarters. So calculate everything out. Again, I'm not going to have you probably calculate the standard deviation from scratch on these problems. I'll probably calculate those for you. But here the means and the standard deviations are already calculated. You have 18 state quarters and 16 traditional quarters, right? So this would be N1 and N2. So remember, if we're going to do a comparison of the t-score, we'd want to do we'd want to look at the t-score with 15 degrees of freedom, right? Because 16 is the smaller of 18 and 16. So we'll use 15 degrees of freedom. So if we look at the t-value at our alpha level, right, that gives you 1.753, which is right here. And so our t-value is sufficiently far away from the mean, so we would want to, it's in the critical region, so we'd want to reject the null hypothesis if we're using the classical approach. So remember, the classical approach, right, you're comparing the t-values or the z-scores, not the actual areas. And again, in the p-value approach, again, we're not going to calculate the p-value here exactly, but it's pretty small. The p-value would be approximately 0.01. Again, you could get a better approximation using a computer like StatCrunch or something like that. But again, it's still less than our level of significance, which was 5% or 0.05. So we will, using either method, we'll reject the null hypothesis. One thing to note here is the degrees of freedom used to determine the critical values in the last example are relatively conservative. A better estimate for the degrees of freedom would be given by this equation, but this is kind of a complicated equation, so I don't think I'll probably have you guys use that too much. But just be aware that if you're doing something that requires results to be relatively close, with a relatively small errors, this is what you'd want to use. So objective 2 then in this case would be to construct and interpret confidence intervals regarding the difference of two independent means. So in this case, certain conditions should be met, right? N1 and N2 should be greater than 30. And in this case, the alpha confidence interval in this case will be given by this formula. So sort of similar to the formula we saw for the test statistic, right? This is similar to the bottom we saw. And again, you're basically subtracting and adding the same thing. So you might want to compute this, and then just subtract this number from that, and then subtract that number from that. So let's look at an example. So we want to construct a 95% confidence interval about the difference between the population mean weight of the state quarter versus the population mean weight of a traditional quarter. So in this case, our alpha level will be 0.05 or 5%, because 100% minus 95% is 5%. And we've already verified the populations are approximately normal. We've calculated these values in the last example. We were calculating the t-statistic. From table 6 with alpha equals 0.05, again with 15 degrees of freedom, we'll find that t alpha over 2, in this case alpha is 0.05, so this would be t of 0.025, with 15 degrees of freedom is given by that. And then calculating this out, again, you'll have the same thing here and here, same thing here and here, So just calculate this, subtract it from that, and then just add here, and you'll get that these will be our two values here. So the difference in means then in this case, so we're 95% confident that the mean weight of the state quarters is between 0.086 and 0.0974 ounces, more than the weight of the traditional quarters. Since the confidence interval does not contain 0, we conclude that the state quarters weigh more than the traditional quarters. So this would be a third way, I guess, you could test the whether to accept or reject the null hypothesis, though typically we'll be either using the p-value or the classical approach, but you could also use the interval approach as well, but we won't really emphasize that. When the population variance is used to be equal, or assumed to be equal, the pooled t-statistic can be used to test for a difference in means for the two independent samples, and the pooled t-statistic is computed by finding a weighted average of the sample variances and using this average in the computation of the test statistic. And so the advantage to do this test statistic is that it exactly follows students' t-distribution with n minus 1 plus n sub 2 minus 2 degrees of freedom. The disadvantage to this test statistic is that it requires the population variances be equal. So if the population variances are equal, right, you could use this. But we won't really talk about that too much anyway, so you don't really need to worry about that. But so that should pretty much end section 11.3, and that ends our discussion of inference about two means. So the last thing we have to talk about then is the inference about two population standard deviation or two variances. So just like in the last chapter, right, we talked about the proportion first and then the mean and then the standard deviation. So in 11.4 we'll talk about the inference about two population standard deviations, which will again involve the F statistic. So hopefully that makes sense. If you guys have any questions, as usual, don't hesitate to contact me, right? Thanks.